All right. Today we want to talk about making a matrix diagonal as best as we can when we have a complex eigenvalues. So, and our matrix is still with real coefficients. So A belongs to R n by n. In one other video, we talk about making a matrix diagonal when all the eigenvalues are real and are distinct. So this time we want to talk about a matrix that might have a couple of eigenvalues that are not real, but all the elements in the A is real. So the way we find eigenvalues is that, remember, we have a u equals to lambda u. Then we bring everything to that side and factor out lambda. And don't forget that we ought to have one I here because otherwise we would have a matrix minus a number, which is not possible. This equals to 0, and the determinant of this, we set the determinant equals to 0. Why? Because we are looking for non-zero eigenvectors. For 0, a times 0 equals to 0 times 0. It's obvious, so that is not eigenvector. We are talking about non-zero eigenvectors. Eigenvalue can be 0 for non-zero eigenvectors. So we might have, for example, a multiply some vector, it turns out to be 0. But we are talking about non-zero eigenvectors. So we set this determinant equals to 0. Now, the thing is that when all the coefficients are real, this becomes a polynomial degree n polynomial, because we would have n by n matrix, and we would have a11 minus lambda, a12, and other coefficients, right? And we would have a22 minus lambda, and all the other coefficients, and we make the determinant, and we would have a polynomial in degree n in terms of lambda. And then we have a polynomial which is real, which has all the coefficients are real. Then when we have complex roots, they come in pairs as complex conjugates. Why? Because if one complex number, let's say sigma I plus I omega I, if this satisfies that polynomial, for example, we would have a polynomial in degree n, let's say a n minus 1, let's say a n lambda n minus 1, and all the others. So if this satisfies this equation, also this should satisfy that equation. Why? Because complex conjugates, when we make it to the power of 2, for example, this would be sigma I to the power of 2 minus omega I to the power of 2 plus 2I omega I sigma I. And then we see that if I have negative here, everything would be the complex conjugate of what we had before. So the real part wouldn't matter. The imaginary part would just flip and it becomes negative. So the same thing for power of 3, 4, addition by number, multiplication. So this complex conjugate is preserved through power multiplication and stuff. So if one of them makes this 0, meaning that the real part is 0 and the imaginary part is 0, so what we get by this, putting this into that equation, if I put this into that equation, let's say at the end I get some number C1 plus some complex number C2. Let's plug in this, the positive part here. Then I get at the end that. And we know that this is 0, so C1 is 0, C2 is 0. If I put this in that, it would be negative. So I know that C1 is 0, C2 is 0, so this is also 0 with negative. So long story short, the complex roots come in pair, meaning that, let me erase it, meaning that the eigenvalues are complex conjugates. They come in pair. And that is the thing that we use to make it simpler. By the way, I should mention that if I have eigenvalues, eigenvalues that are complex, I can still make it totally diagonal by using eigenvectors, but that diagonalized matrix, it would have complex numbers on the diagonal, and we want to do something else ultimately with this diagonalized, or sort of semi-diagonalized matrix. We want to do exponential. So that is better to have, to not deal with complex numbers, to not deal with imaginary part of the complex numbers. That's why, so let me erase this part as well. So what I'm saying is that the eigenvalues, let's say they are lambda 1, lambda 2, and lambda, let's say L, and then sigma 1 plus I omega 1 plus minus. Remember, they come in pair all the way to sigma m plus minus I omega m. And then n is L plus 2m. Because we ought to have n distinct eigenvalues, L of m are real, and 2m of m, they come in pair. 2m of m are complex conjugates, so we would have n equals to that. We still can make this diagonal by stacking eigenvectors next to each other, and then the eigenvalues would sit on the diagonal. Watch the other video that I have for eigenvalues of real distinct eigenvalues, when how to make a matrix diagonal when we have real distinct eigenvalues. The same thing works for if we have complex, but we don't want to have complex eigenvalues sitting on the diagonal. Ultimately, we can prove that if I have some u that I will define later, a u, then my diagonal matrix would look like this: lambda 1, lambda 2, and then lambda n, L, and then blocks of sigma 1, omega 1, negative omega 1, sigma 1, sigma 2, omega 2, negative sigma 2, omega 2, and they're all, the rest are 0. So it is not, it is a block matrix, block diagonal, meaning that we have some exact diagonal and off diagonals are 0, and these parts are blocks of matrices, and all the rest are 0 here, right? So we would have 0, except that we would have this. So the reason that we like to have it this way is that we can calculate e to the power of this matrix easier. And that is the topic of another video. But our goal here is to make a diagonal matrix that looks like this, all right? How to do that? Well, first of all, let's show that if my eigenvectors, let's say eigenvectors corresponding to lambda 1, lambda 2, lambda n are u1, u2, and ul, all right? Then the eigenvectors corresponding to this one, let's call them v1 plus minus I y1, and all the way to Vm plus minus I ym. Now you might think that, okay, we showed that the eigenvectors come in pair, right? But who guarantees that the eigenvalues come in pair? Who guarantees that eigenvectors are also come in pair? Well, we can show that that eigenvectors come in pair, but just in a moment. Then we make that U matrix U as this U1 as the first column, then U2, then UL, then V1, just a V1. This is a real vector. This is also real vector multiplied by that I. So we put Y1 next to that, then V2, then Y2 next to that, all the way to VM, Ym next to that. And this matrix U makes, if we do this U inverse AU, it makes it as a block diagonal matrix. So we would have diagonal, and this matrix is this blocks on the diagonal. So this is that U that we are looking for. So we want to show that. Well, first, let's show that these eigenvectors are also come in pair. Well, if I have A times at V1 plus I, let's say VK, I YK. Let's say this is an eigenvector corresponding to that eigenvalue, sigma k plus I omega k. Then this would be Vk plus I yk, right? Because this is an eigenvector, it means that A times that eigenvector becomes that corresponding eigenvalue times that vector. Now, the real part of this, remember, A has just the real components. So the real part would be AVK. This time, this side, it would be sigma K VK minus omega K YK. And the imaginary part would be AYK, again, because A is just a real coefficient. So what is imaginary is just here, embedded here. There is nothing here, nothing here. So if we have that, it would be AYK equals to the imaginary part, the same here. It would be omega K VK plus sigma K YK. Now, what if I would have negative here? If I have negative, 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 meaning that look at the negative, the conjugate part. If I put negative here, then negative here, then negative here, then everything would be the same because the real part was not changed anyway, right? It has negative I times negative I, which is again negative 1. And this part, that part. And for complex part, the same thing. So meaning that if the positive satisfies these two equations, the negative also satisfies these two equations for sure. So it means that if that positive part is the eigenvector for that positive part of the eigenvalue, then the negative would be also the negative part. So you can think about it that if I replace this positive with negative, nothing would change. So if this holds true, the negative should also hold true. So if this is the eigenvector corresponding to this eigenvalue, the negative part, the complex conjugate part of that, is the corresponding eigenvector to the complex conjugate part of the eigenvalue. So eigenvectors also come in pair. So this makes sense, at least for now, that we stack them like this. all right? And because they come in pair as well. So now, remember that, I mean, it is discussed in another video that if I have some A matrix, all right, and let's say A is first column, I call it A1, then second column, I call it A2, ith column, I call it AI. If I multiply it by EI, this would be just AI. Because EI, it is 0, 0, 0, and 1 is at the ith row. And then again, 0, 0, 0. And when we multiply that, rotate, multiply this way, then the ith component is multiplied, the ith column is multiplied by 1. All the other columns are multiplied by 0. So that's why when we multiply this by EI, we get AI. Now, I can say that if I multiply it by, let's say, just want to make room for two vectors. So if I multiply by, let's stack EI and EJ next to each other, or EI and EI plus 1, then it would be 2 columns and AI plus 1. So if I have two vectors like that, again, because only the ith component and I plus 1 component is multiplied by 1. In fact, instead of I plus 1, I could have j. So EI, EJ, I would pick just 2 columns, ith columns and jth columns. All right, so now let's erase this. So let's look at this. A, U, and then we stack them by EK, and let's say let's pick some number, EJ and EJ plus 1, all right? Let's say the jth column here, the jth column, because the jth column can correspond to the K for V and Y. Because remember, we have all the way to L, and then we start counting again, 1, 2, 3. So we pick the jth column, and let's say the jth column correspond to VK, all right? So this would be A, we stack U this way, because so far we saw that the eigenvectors are coming in pair, so we can make U this way, and we would have N columns. We want to show that this becomes this. So far, we know that we can make U that way. And the jth column would be, let's call it VK, somewhere there, all right? So this would be VK and YK, all right? AVK, we have it here. AYK, we have it here. So we can write this as sigma K VK minus omega K YK, and then omega K VK plus sigma K YK. And this is just one column. Whole thing is just one column. This is one column, one column. Now we separate these columns and we write it as sigma, let's say sigma k vk, this is column, right? And yk plus omega k, then we write it as negative yk, and then vk. The reason that I put this vertical line is just to say that this is a column, all right? Now, if I multiply a by, you see, I multiplied that a by that already. Now, let's look at u again. U at ek, ej, ej plus 1. This becomes, use the other color, vk yk. So if I multiply both sides, let's make some room here. If I multiply both sides by u inverse, then this becomes I, right? And this becomes the thing that we want to have. So you see, I have AU times this whole thing becomes this. So it means that, I mean, if I look at 1, let's call this 2 and 1, then it means that U inverse AU should be U inverse, let's say sigma K, U inverse this one plus omega K, U inverse negative YK VK. Now we have that EJ plus 1 equals to U inverse of this, right? So in other words, this equals to EJ plus 1. How about this one? For this one, we can switch these two, EJ plus 1 and EJ. Then I would switch that, right? And then, so uh, let's do it here. So I'm saying that U negative EJ plus 1, I just multiply by negative EJ. This would be, I pick the J plus 1 column first, which is YK. and then multiply by negative, and then j column, which is vk. Then I see that if I multiply by u minus 1, then this would be I, this would be that. So this would be, I mean, up to this part, would be negative ej plus 1 ej. So at the end, we get u inverse au. This equals to sigma k ej plus 1 plus omega k negative ej plus 1 ej. And these are all columns. In other words, it would be, I would have 0, 0, 0, all the way up to the j, which is 1. Then I would have sigma k. Then the same column, because this is two columns, the same column, one below, I would have negative omega k, and then bunch of zeros again. Then for this one, at k plus 1 row, I would, j plus 1 row, I would have sigma k. At j row, I would have omega k. And the rest are 0. So I have two columns like that. So if I multiply that, by the way, I forgot to put ej. This is u inverse a u ej plus 1. So the jth column and j plus 1th column is that. Then we can go to the next. Then we stack them up, and this time it would be 2 below, then 2 below that. So at the end, we will see that, all right, so if we do that, repeating that, we will get that matrix that we would have lambdas, that real ones that we don't talk about here, let's say all the way to lambda L, and then we would have sigma 1, omega 1, negative omega 1, sigma 1, and then this is like a block, and then the next block all the way. All right, so long story short, when we have complex eigenvalues, they come in pair, both the eigenvalues. By the way, when we are talking about a matrix with real coefficient and distinct eigenvalues. So if they are complex, we could do the same as before, but this diagonal, it would have complex eigenvalues on the diagonal. But we prefer to work with real numbers. Not everything is real in this one. Even though it is not perfectly diagonal, it is blocked diagonal, which means that we have some blocks on the diagonal. You can watch the video that is about a matrix exponential, and you will see why we prefer this one. So if we have complex eigenvalues, then eigenvectors also come in pair, complex conjugates, and we stack them up this way. First, the eigenvectors for the real ones, and then for the complex one, this part and this part, the real part and the imaginary part, with that I. So it is also, these numbers for y is also real. So we stack them up, and then when we do this u inverse au, we get this matrix. Don't forget that we can replace this u and v and switch them, so this would go up and the real eigenvalues would sit down. It doesn't matter. Or I can make this pair come there, then this block would move one up. So at the end of the day, it would look like this, some numbers on the diagonal or some blocks that exactly look like this. A number, real number, negative of that number, and the same number here. And it is easy to calculate the exponential of this one, which is the topic of another video. All right, thank you.